All, welcome back to my YouTube channel all about VLSI. In this particular session, let us try to develop an asynchronous FIFO for our Ethernet MAC controller. Now, first of all, before developing an asynchronous FIFO, we need to understand what exactly is asynchronous FIFO, what is a problem which we were facing, and how this asynchronous FIFO is helping us to resolve the problem, right? Now, first of all, let us try to understand the problem which we are facing, right? Now, let's consider a scenario where if we have a device A, this is my device A and this is my device B. Now, this particular device A and device B are having a same clock. Now, what do I mean by the same clock? Same clock in the sense both the devices are working with the same clock frequency. Let's say clock frequency here it is 100 megahertz. Then the device B clock frequency is also 100 megahertz. Then this two devices are said to be synchronous in nature. So these two devices are basically synchronous in nature. Okay, fine, that's very good. Now, what is going to happen if these are two are synchronous in nature? Then, if device A is sending some particular data, then device B can sample that particular data without any data loss because both are having same clock frequency provided that here device A is let's say it is writing with a speed of 50 megahertz and device B is also reading the data with a speed of 50 megahertz, and I will write down over here. So writing speed is equal to reading speed, then there is no problem at all. Okay, so let's say if device A is writing at the first passage of clock, then device B can read the data at the second passage of clock. If device A is writing the data at the first passage of clock and device B can read the data at second passage of clock, then there is no problem at all. But where will be the problem arise is if device A can able to write the data only not only one data item, it can write two data items at first passage of clock, but device B can only read first data item at first and second passage of clock and third and second data item at the third passage of clock. And meanwhile, what is device A is going to do? Device A is going to write down two more data items. Then you are basically losing one data item in the device B. Okay, so this is where the problem occurs. If clock frequency in both device A and device B are same, but if the writing speed and reading speed are different, like if your device A is writing at the speed of two data items per clock, but if device B can only read one data item per clock and it is basically losing another data item, by which by then your device A is basically writing other another two data items, then there is a loss of data. Now in this particular case, what you're going to use, you're going to use a FIFO. So we have a device A and we have a device B over here, and we have a FIFO over here. This FIFO is going to temporarily hold the data. So device A is basically writing with very high speed and device B is basically reading it at very low speed. Then in this particular case, FIFO is going to temporarily store the data and device B is going to fetch out this particular data from this particular FIFO at its own speed, and device A is going to write down the data into this particular FIFO. And we have a number of times discussed in our channel regarding what do you mean by FIFO. And whatever the FIFO which we are going to use over here, it is a synchronous FIFO. Why it is a synchronous FIFO? Let us try to understand. So we have a device A over here. This is my device A and this is my device B. Now, if we have learned about FIFO previously, then you might have known that we have a clock and reset. Now, what is this clock? This is the same clock which was connected to my device A as well as device B. And the reset is also provided to device A and device B. Now, we have one more signal which is known as write enable. Now, what is this write enable is used to? Write enable is basically used to enable the data write operation into this particular FIFO, and read enable is basically used to read the data from this particular FIFO. Now, who is going to provide this write enable and who is going to provide this read enable is understanding this is also very, very important. Write enable is provided by my device A and read enable is provided by device B. That means the whoever is reading the data, they are going to provide this particular read enable, and whoever is going to provide the writing operation, or whoever is going to provide the data, they are going to provide this write enable. And we also know that internally, a FIFO is going to have two pointers. One is write pointer and another is read pointer. If you're a person who don't know anything about FIFO, I recommend you to please go through the FIFO series which we have discussed in a great detail about synchronous FIFO, so that you will come to know what exactly is a synchronous FIFO and what I'm talking about, right? Now, in this FIFO, internally it is going to have something known as write pointer and read pointer. Now, whenever device A is going to provide this write enable, write pointer is going to increment itself. Okay, like write pointer, it will be 0, next it will be incremented to 1, next it will be incremented to 2. And whenever the user is providing read enable, read pointer is going to increment itself. That means read pointer will be equal to 0, and read pointer equal to 1, and read pointer equal to 2. Now over here there is no problem, because device A and device B are connected to the same clock, and write pointer and read pointer are incrementing with respect to the same clock. Here both write pointer and read pointer are incrementing with respect to the same clock. So we have two more signals like full and empty conditions, which we are going to get it from the FIFO, which are also going to become true whenever this write pointer and read pointer, or whatever the conditions which we have written for full and empty conditions, right? So there will be no problem at all. And over here, device A is having the same clock and device B is also having the same clock, and write pointer and read pointer are incrementing with respect to same clock. Then there is not at all a problem. Now, the problem arrives where, let's say if I have a device A and device B. Let's say I'm going to use a FIFO over here. Now, this device A is going to have a high frequency clock. So device A is going to have high frequency clock with it, and device B is going to have a low frequency clock with it. That means device A is having separate clock and device B is having separate clock. In this particular case, I am not supposed to use a synchronous FIFO. Here, I am going to use something known as asynchronous FIFO. So in the case of my asynchronous, why I should not use a synchronous FIFO? Because in the case of my synchronous circuit where my device A and device B were having same clock, so FIFO was also having the shared clock which device A and device B were using, and there was no problem at all. Okay, and writing was happening with respect to one single clock, and reading was happening with respect to the same clock. Okay, which device A and device B were sharing. So there was no problem at all. But in the case of this particular scenario where device A is having high frequency clock connected and device B is having low frequency clock connected, how are we supposed to use? So should we make the write operation and should we make the read operation to with respect to which particular clock? That we should select, right? Now over here, in the case of my asynchronous circuit, write operation is going to happen with respect to high frequency clock. So here I am going to have high frequency clock, and device A is going to perform the write operation. So write operation is going to perform with respect to high frequency clock, and device B or the read operation is going to happen with respect to low frequency clock, and device B is going to provide the read enable with respect to this low frequency clock. This is what your asynchronous FIFO is going to happen. In the case of your synchronous FIFO, write operation and read operation is happening with respect to a single clock, and the clock was shared to device A, device B, and the FIFO. But in the case of your asynchronous FIFO, write operation is going to happen with respect to high frequency clock, and read operation is going to happen with respect to low frequency clock. Now, let us go back to synchronous FIFO again. In the case of my synchronous FIFO, if you have learned about synchronous FIFO, you might have known this particular condition: empty is equal to write pointer, which is equal to read pointer. If this condition has satisfied, then empty was equal to 1. And right pointer was incrementing from 0, 1, 2, 3, so on with respect to a clock, and read pointer was also incrementing like 0, 1, 2, 3 with respect to the same clock. So write operation was happening with respect to the same clock, and read operation was happening with respect to the same clock. So we are going to basically track this empty condition very easily. Empty condition, finding out whether the FIFO is empty or whether FIFO is not empty, was easier because both the devices were working with the same clock. Now what is going to happen here? Device A is basically writing the data into the memory with the high frequency clock, and device B is basically reading the data with low frequency clock. Now, what is going to happen over here? Let us try to understand. So, let's say in the case of my asynchronous FIFO, if I want to find out the full condition, if I want to find out the full condition, now which particular device is going to check for this full condition? Device A or device B? Device A. Device A is going to first of all check this particular full condition. Whether this FIFO is full or not, device A is going to check. Then only it is going to provide this write enable. And device B is going to check for this empty condition, whether this particular FIFO is empty or full. If it is empty, then it is not going to read. If it is not empty, then it is only going to read. Now, how to generate this particular full condition? We can simply write pointer is equal to read pointer. No, we cannot write. Why we cannot write? Because write pointer incrementing happening. So write pointer is going to increment itself with respect to high frequency clock. This is going to happen with respect to high frequency clock. And read pointer incrementing is happening with respect to low frequency clock. This is happening with respect to low frequency clock. So that means the right hand side, or the device who is basically writing the data, is not going to have the information of read pointer because it is working with high frequency clock. This particular side is working with the high frequency clock, and read pointer is happening with respect to the low frequency clock. So what is the requirement over here? The read side or the device B side should send the data or the read pointer information to the right side. So for calculating the full condition, because here read pointer is working with respect to the low frequency clock, and write pointer was working with respect to high frequency clock. So read pointer which was working with respect to low frequency clock, that particular information, the read pointer information, should be shared from low frequency clock domain to high frequency clock domain. So the read pointer which is present in the low frequency clock domain should be shared to high frequency clock domain, so that write pointer and read pointer can be compared and we can provide the full condition. That is the requirement over here. Let me repeat my requirement again. Read pointer incrementing which is happening in the low frequency domain should be shared to the high frequency domain, so that write pointer and read pointer can be successfully compared and full condition can be given to the device A. Similarly, if I want to provide the empty condition, then I have already, in the low frequency domain, I have read pointer available already, because read pointer is basically implemented in the low frequency domain. But write pointer is implemented in the high frequency domain. So this particular write pointer which was implemented in the high frequency domain should be passed to the low frequency domain, so that this write pointer and read pointer can be compared and this empty condition can be given to the low frequency domain. This is the requirement. So this process is known as clock domain crossing. Basically, we are passing the write pointer information and read pointer information. Let me once again explain this particular thing. So here we have high frequency domain on the left hand side, and we have low frequency domain on the right hand side. So write pointer is basically implemented with respect to high frequency domain. Why write pointer is implemented in the high frequency domain? Because user A or the device A is providing write enable with respect to this high frequency clock. So when you're providing this write enable, obviously write pointer is going to increment, right? So in the high frequency domain, if the user is providing write enable, then obviously this write pointer is going to increment. So that's the reason write pointer is being incremented in the high frequency domain. Whereas low frequency domain, device B is providing read enable signal. So that's the reason read pointer is being incremented in the low frequency domain. Now, what is going to happen in the high frequency domain? Device A is working. Device A is working in the high frequency domain. Now, it needs the information of full condition. Device A needs the condition of full condition. Now, how we are going to calculate full? We already have the right pointer information because it has been implemented in the high frequency domain. We need the information of read pointer which is being implemented in the low frequency domain. So this particular read pointer should be given from this low frequency domain to this particular high frequency domain so that we can able to compare, we can basically able to get this full condition and so that we can give it to the device A. Now, similarly, empty condition, which should be given to our device B, which is working in low frequency domain, already have read pointer information available. Okay, but it needs write pointer also, right? But this write pointer is being implemented in high frequency domain. So this particular write pointer should be given to this low frequency domain so that my low frequency domain can compare this write pointer and read pointer and can generate this empty signal information. So that is this particular process is known as CDC, which is nothing but clock domain crossing. So this is what we are going to do. So simple. In the asynchronous FIFO, we are going to basically transfer the write pointer from one clock domain to another clock domain for calculating empty condition. And we are going to pass read pointer from one clock domain to another clock domain for calculating full condition, right? Now, what is it we are going to have? What is the problem which is going to arise in this particular CDCs? Let us try to understand. So let's say here our write pointer is in binary format and read pointer is also present in binary format. Let's assume these two are present in your binary format. Now, what is going to happen if these are two are present in binary format? Let us try to understand. And this write pointer is being implemented in high frequency domain, and this is being implemented in low frequency domain. And if I want to calculate full condition, if I want to calculate full condition, then what I have told you, I have write pointer information already present with me. Okay, I should get read pointer information from this low frequency domain. Now, let's say this is my high frequency clock. This is my high frequency clock, which is that I'm going to have, right? Let's say read pointer was initially 000 something, which was sampled at this first passage of clock without setup time and hold time violations. Okay, let's assume there is no setup time and hold time violations and it was sampled at first passage of clock. Now, let's say the next data is 001, which is also sampled without any setup time and hold time violations. Let us assume that there is no setup time and hold time violations while sampling this 001. Okay. Now, during this particular transition 0002 to 001, when we are getting this particular 001 information, let's say at this particular second edge of clock, there was some setup time violation or there was some hold time violation because these are two are different clock domains, right? Let's assume that while sampling this particular 001, there was some setup time violation. Okay, there was some setup time violation. Now what happens? So 00 was already present. 000 was already present. The last bit was getting transition from 0 to 1. So this transition was not properly captured by the right high frequency clock domain, and due to this there is a metastability in this particular bit. So let's say 00, and due to this metastability the last bit will be metastable, that is it is unknown, and after some time this will be stable. Let's say if it is settling to 0, then no problem because we already have this information 000, or else let's say it is settling to 001 also, then it will be no problem because this is what we want. Okay, so again, repeating myself again, what is happening? This particular high frequency clock domain is trying to receive this particular read pointer information, and initially it got 000 without any setup time and hold time violation. Okay, fine. But when receiving the next pointer information, which was 001, this is 001, and 001, you can observe there is a transition at the last bit. Now let's say if this transition is happening, and this transition is happening at setup time or hold time, if this particular transition is happening below the setup time or hold time, then there will be setup time violation. Let's say if there is a setup time violation, then this particular transition is not properly captured and it will enter into metastable state. The last bit is going to enter into metastable state. Let's say it has entered into metastable state, and after that it is going to settle to 0, then also no problem. It is a valid pointer value. Or else if it is settling into 1, then also it's not a problem because that is what we want. Okay, there is no problem over here. Now, let's say the next pointer value is 010. So 001 to 010. This is what our transition is, 001, 010. Now, what is going to happen here? Here, two bits are changing. This last bit is changing, and before bit is also getting transition. Now again, let's assume that there is a setup time violation while this transition is happening. Okay, let's say if this transition is happening at exactly at this positive edge of the clock, then obviously there is a setup time violation, right? Okay, or if there is a transition happening from 1 to 0 at the exact positive edge of your high frequency clock, then it's a setup time violation, right? And let's say setup time violation has occurred. So what is going to happen? So what is going to happen? These two bits will be entering into metastable state. Okay. Now after some time they will be entering into stable state. Now what is going to happen? Let's say the values they are going to enter as a stable values. It might be 00, or it might be 001, or it might be 010, or it might be 01. See how much ambiguity which is present over here. So read pointer can be any of these particular values. Okay, because they have entered into metastable state, they can be any values after getting stable, right? This is a major problem if we are going to use our binary pointers. That is the reason we are going to use gray pointers. See, if we can use a gray pointer, then obviously for each and every adjacent numbers, there will be only one bit change. And if there is only one bit change, you can see if there is only one bit change, there is no problem. It may be the previous value or it may be the present value. That's it, right? So if we are going to use a gray pointer, then this particular metastable condition or the ambiguity condition which we were having will be completely erased. Okay, so that is the reason we are going to prefer gray pointer when we are going to transfer this particular read pointer values from one clock domain to another clock domain, or write pointer values from one clock domain to another clock domain. We are going to convert them into gray code and we are going to transfer. And that is the reason we are going to use this particular gray code. And we can also remove this particular metastable condition which we were having over here, which we were facing over here in the case of our gray pointers. I'm not stating that in the case of my gray pointers, I'm not going to get any metastable condition. No, I may enter into metastable condition, but that particular condition, if it is being resolved after some time, this particular pointer, read pointer value, it might be the previous value or it might be the present value. But if we are using binary pointer and if you are going to enter into metastable state, if it is being resolved after some time, it is going to have multiple possible combinations which will be ambiguous, and you might get wrong, full, or empty conditions, obviously, right? So that's the reason we are going to use our gray pointers. Now, so let's say if we are going to use gray pointer, let's say we are basically converting this read pointer into gray information and we are passing it. Okay. Now, it also might enter into metastable state. Now, let's say if I want to remove this particular metastable state also, then what I'm going to do is I'm going to use a 2D flip-flop synchronizer. So this 2D flip-flop synchronizer I'm going to use, and this 2D flip-flop synchronizer, the first flip-flop is connected with the source clock 1 and the second flip-flop is connected with source clock 2, that is the receiver's clock. Now, what is going to happen? Let's say if the sender has sent a particular D flip input to this particular flip flop. Okay. And what is going to happen? Let's say we are entering into metastable state over here. And after some time, this particular bit which was sent to this particular flip flop is entering into metastable state. Sorry, this is also connected to the receiver's clock. Okay. So let's say if the bit has been sent to our first flip flop and it has entered into metastable state. Okay, not a problem. After that, it should enter into a stable state, right? It will go into stable condition. So this particular stable bit will be sampled by the second flip flop. That's it. So this is how we are going to remove our metastable condition. Okay. Yes. So this is how a asynchronous FIFO is going to work. And if I want to draw the block diagram of your asynchronous FIFO, this is how it is going to look like. So we are going to have a FIFO which is present over here. And this FIFO is being connected with data in. So the sender is providing the data in, is going to provide write enable, and he's going to provide write clock, and this FIFO is going to give me the full condition. Okay. And this full condition is being given by a particular module which is basically write pointer handler. Okay. And this particular write pointer handler is going to give me the full condition to the FIFO as well as to the user. Okay. And I'm going to have on the read side a read pointer handler, which is basically going to, give me the empty conditions to the user as well as to the memory. Okay. And from here, I'm going to give my data underscore out, and read enable, I'm going to provide it, and the receiver's clock, we're going to give it over here, and empty condition is being given. Now, write pointer handler is already going to have the information of, you know, write pointer handler is also already going to have the information of write pointer. So for calculating the full condition, it needs read pointer information, which is being given by your read pointer handler, which is being converted into gray format, g underscore read pointer, which is being converted into gray format, and it is passed via a 2D flip-flop synchronizer. So it is passed via a 2D flip-flop synchronizer, and it is given to this write pointer handler. Similarly, write pointer handler is going to give the read pointer handler what information it is going to give the write pointer information in gray format. And it is also passed via a particular 2D flip-flop synchronizer. So this is how a FIFO, a asynchronous FIFO is going to work. Okay. Anyways, we are going to deal in great detail like how we are going to implement it and all. It's not an issue. But the major part over here to understand is in the case of your synchronous FIFO, your write pointer and read pointer were incrementing with respect to the same clock. So you're not having any particular issue. You are incrementing them, you are playing with them. But in the case of your asynchronous FIFO, your write pointer was incrementing with respect to the high frequency clock. In this particular example, it's high frequency clock. It may be low frequency, and on the receiver side, it may be high frequency. For example, I have took write pointer was incrementing with respect to device A clock, and read pointer was incrementing with respect to device B clock, which is basically different with each other. Now, what should happen in the case of your synchronous counter? Full condition was calculated using write pointer and read pointer. There was no issue because write pointer and read pointer was incrementing with respect to same clock. But here, in the case of my asynchronous FIFO, if I want to calculate full condition, I already have write pointer information which is present on the device A clock domain, but I want read pointer information which was implemented in the read device B clock domain. So that particular read pointer information should be passed from device B clock domain to device A clock domain. So in this particular clock domain crossing, I will face few problems, and the solutions for that particular few problems have been discussed over here. Okay. Yes. So that's about this particular session. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.